UCT. Jeff is going to give you a special lecture on solitons.
Thanks, Clifford. Okay.
Welcome, Jeff.
It's good to be here. Glad. Okay, so I want to talk to you a little bit about solitons. So before I start, let me tell you what mine and probably everybody who's studied the subject's favorite book on solitons is. It's a really good reference, and I recommend it. It's called Solitons. And Instantons, an introduction to the study of solitons in classical and quantum field theory. Okay, so when I first learned about solitons, I learned it from and like many people in the audience here today, I learned it from a Russian professor in this department. And this particular Russian professor in this department is particularly fanatical about solitons. To the extent that I remember one Saturday afternoon we were playing tennis together with his family. And for anyone who knows, it was at the Sachs tennis courts. And the thing about the Sachs tennis courts is that they have this drain system sort of at the end of the tennis court. And it's one of these things that kind of has the tap here, and the drain goes like that, and like that, and like that. All right, so it goes down this hill thing. And halfway through, so his 8-year-old son is sort of with us. And halfway through the match, the son stops the play and says, Dad, soliton. And what he was doing was running water down here. So the water comes down and flows down this trough thing. And he'd stop the water and he'd build up a little bit here, and then he'd let it go, and then it would fall down. And sure enough, it actually was a soliton. So this is a shallow water trough, and the differential equation that governs shallow water waves in narrow troughs is something called the Korteweg-de-Vries equation, and he was making Korteweg-de-Vries solitons. And he's an 8-year-old kid. So among the things that I learned from his father was that solitons are absolutely ubiquitous. They're universal. They occur absolutely everywhere. They occur from D-branes to DNA, from superfluids to tsunami. All of these things can be described to very good approximation by solitonic objects. I guess the point of telling you this is that the literature on solitons is absolutely massive. It's huge. I have no hope in hell of telling you all that everybody knows about solitons in 1.5 hours. So what I'm going to do is tell you a little bit about something that's almost a soliton. It's not really a soliton. But for the first year or so that I'd heard about the subject, I thought it was a soliton. So I'm not going to do much harm by just insisting that it is a soliton. Now, I hope that the little bit that I can tell you in this 1.5 hours will whet your appetite, and you go off and read Roger Raman and come away knowing something a little more about solitons, where they occur, and how they're useful. There's a couple of ways we could proceed from here. One is I could give you a formal definition, tell you what the soliton is, and then just try and find something that fits within that definition. But I would rather take a more exploratory approach. So we'll write down an action, we'll vary the action, we'll get an equation of motion, and we'll see if we can solve that equation of motion to get some interesting solutions, and then we'll look at the properties of the solution and see whether or not it fits into anything interesting. Okay, so there are some people in the audience who've taken a 1-year course in solitons, I happen to know. And this will be extremely boring for them. So if they could humor me and at least try to not snore too loudly, I think we'll get on fine. Okay, so I want to write down an action. I think we'll start off in the simplest case of 1 plus 1 dimensions. Okay, so we're working in one spatial dimension and one time dimension. Space for us will just be the real number line. We go from minus infinity to plus infinity. And we've got one time dimension, and just so that I'm setting up my notation, the metric I'm going to be using this 1 plus 1 dimensional space, g mu nu, will take this form. So it's flat Minkowski 1 plus 1 dimensional space. By now, everybody knows what a metric is. The action, well, the action we know is the integral over this 1 plus 1 dimensional space of some Lagrangian density. And generally, the Lagrangian density is a function of a field. And I'm going to be worried about scalar fields, just one scalar field, and derivatives of the scalar field. So the Lagrangian that I'm going to use is going to be the simplest I can construct. I have a kinetic term, and I subtract from it the potential term. You know that this is how Lagrangians work. I have kinetic energy minus potential energy. The kinetic energy, well, the kinetic term is going to be one half d mu phi minus some potential. Hopefully by now everybody's clear with this notation. The mu, one downstairs, one upstairs. Like Professor Gates told you yesterday, the altitude's important. When I have one downstairs, one upstairs, then I'm summing over the range of this mu. Mu goes from 0 to 1. This means that it's d naught plus d1, d1. Okay. Right, so explicitly, I can write this out as 1 half d naught phi, d naught upstairs phi, plus a half d1 phi, d1 phi minus this potential. Now, what the metric says is that if I drop this index, because there's a plus 1 here, no change in sign. When I drop this index, because there's a minus 1 here, it comes with a change of sign. So let's do that. Okay? But d naught is a bit of a silly thing to call this. So let's just say it for what it is. That's dt. And d1, of course, means d by dx. So I'm going to call it dx phi. All right? Now, of course, I can make this notation a little more compact and just call this thing 1 half phi dot squared minus a half phi prime squared minus this v of phi. So that's the Lagrangian. Okay? So there's two things we note about the Lagrangian. One is that it has this very special form where I'm summing over all the Lorentz indices. Okay? The Lagrangian of this form has the property that it's Lorentz invariant. In other words, it describes a relativistic system. So what? Well, the thing about Lorentz invariant systems is that if I find a solution to whatever equation of motion I'm going to get from here in whatever frame, then it'll be a solution in another frame, and a frame that I get from the one to the other by Lorentz transformations. So if I find a particular frame in which it's easy to find a solution, and then I transform by Lorentz transformation to another frame, I'll get another solution. So what we're going to do is not worry about moving solutions. The frame that we're going to pick in which to do all our calculations is going to be a static frame. So I'm only going to be worried about static solutions. In other words, I'm going to kill off this guy because it's a time derivative, and if I worry about static solutions, and static solutions aren't going anywhere, so there's no time evolution, And so my Lagrangian then looks like this, minus a half phi prime squared. Phi prime, by the way, means d by dx, and phi dot means d by dt. Minus 1/2 phi prime squared minus v of phi. But then I've only got static solutions. But then I said if I find a static solution, to get a moving solution, all I've got to do is just boost this guy, right, by Lorentz transformation. So that's the plan. We're going to look for static solutions. Once we have the static solution, we're then going to boost the static solution to get moving solutions. And we're going to see what that implies for everything. Right, so what do you do with an action? Well, from an action, you get an equation of motion. You get the Euler-Lagrange equations by taking the functional derivative. So if I have this action, and I vary the action with respect to phi, that's just the notation that I'm going to use, then what I get is the variation of this guy here, 1/2 d mu phi minus Is this boring for anyone? Do you want me to go through it in detail and then at least once? Okay. Right, so what happens here is that I've got to vary each of these terms. When I take the variational derivative of this guy, I get d2x. So it's delta of 1/2 d mu phi minus delta of v of phi. This is, of course, not the most correct way you can do this. That would involve delta functions, and I don't really want to do that. But this is a nice sort of semi-heuristic way of getting the equations of motion out. Right. So now, this thing acts like a derivative, which means that it's got to obey something like the Leibniz rule, the product rule, which means first it acts on this guy times this thing plus this thing times it acting on this thing. Right? Now, the way these indices work is that as long as I'm summing over them, I can, if I drop one, I can raise and I raise the other one, I'm still okay. Meaning that I get two of the same contributions from this first term. So this is just the integral d2x, 1/2 d mu phi delta d mu phi, plus another one of those will add to cancel up this half, and then I've got to subtract off the variation of this thing. So the way the variation works is that delta of v of phi is dv by d phi delta phi. That's like the chain rule. So now I look at these two terms, and I've got d mu phi delta of d mu phi, dv d phi delta phi. I want to be able to pull out this delta phi here, but I can't really do that because I've got delta acting on this derivative. But the way these things work is that I can interchange the order of the d and the delta. So now I've got I've got the partial derivative acting on this delta. I still can't pull it out because it's being acted upon. So what I've got to do is throw this thing onto this term. How do I do that? I integrate by parts. So if I integrate by parts, I throw the derivative onto that side, and it comes with a minus sign. And a boundary term, but I don't really care about that because I'm assuming my fields are well behaved at infinity, and the boundary terms vanish. So this is the integral d2x. This is after integration by parts, minus d mu phi minus dv by d phi. And now I can pull out this overall delta phi. And then I say, well, this is the variation in the action when I've made an arbitrary variation in this field phi. And the equations of motion come from demanding that that the action be static under this variation. So I want that delta S be equal to 0 for all delta phi. And the only way that's true is if this guy vanishes. Right? So delta S phi equals 0, if d mu phi plus dv d phi equals 0. So that's the Euler-Lagrange equations that I get from here. And so now, I said that I could write my Lagrangian like this. I could have done all of this with this particular Lagrangian that I've only concentrated on the static solutions. But then I can do the same thing down here as well. D mu means I'm summing over the mu, which means this is dt squared phi minus del squared phi plus dv by d phi equals 0. I don't care about time derivatives. So that's my equation of motion. This is the static equation of motion. In other words, it's the equation of motion that describes for me static solutions. I haven't told you anything yet about the potential. I've left that completely unspecified. In fact, I can go through a couple more steps not telling you anything about the potential at all. So I look at this thing, and it's a second-order differential equation which I've got to solve. So I give you a potential. You know how to solve second-order differential equations, so you can go ahead and solve this. I've also got to give you boundary conditions. But there's actually a much neater way of doing this. And to do that, I notice the following. I notice that if I take the quantity a half dx phi squared minus v of phi, and I take its derivative, then by the chain rule, this thing acting on the first term brings down the 2. That gives me a dx phi times the derivative of what's sitting in here. That's dx squared phi minus the derivative acting on this potential. It's, of course, d by dx. This is a function of phi of x, so I've got to use the chain rule again. So it's minus dv by d phi dx phi. And then I've got a common factor of dx phi. So that's equal to the derivative of phi with respect to x times minus dv by d phi. And then I compare this thing to this thing, and the equations of motion tells me that this thing in the brackets here vanishes. So overall, that means that this guy is equal to 0. I have the derivative of something equal to 0. The something's only a function of x. The derivative of something equals 0 means I can integrate that to give me a constant. So if I integrate this thing, I get that the quantity a half d phi by dx squared minus v of phi is a constant. What I've found here is a first integral of the equation. First integral of motion. I have a constant of the motion of this scalar field phi. I have to determine what that constant is, of course, but, this is now a first-order differential equation. So I've at least made some progress in that regard. So how do you determine that constant? Well, again, there's a neat trick to determine the constant. And what it is really what we're doing is working with the Lagrangian so far. There's something else that I can associate to the action, and that's the Hamiltonian. And I get from the Lagrangian to the Hamiltonian by a Legendre transformation. Okay, so from the Lagrangian, I can form a quantity called the Hamiltonian. And the Hamiltonian is what I get when I take the quantity dl by d phi dot dl by d phi dot times phi dot minus L. So you'll remember from classical mechanics that I get from a Lagrangian to a Hamiltonian by going pq dot minus the Lagrangian. Well, this is the same just for the field. So what I've just said is I don't really care about time evolution at all. I'm only interested in static solutions. So this term is equal to 0. For static solutions, the Hamiltonian is nothing but the minus the Lagrangian. Okay? I know what the Lagrangian is. It's just minus a half phi prime squared minus v of phi. Minus that is just a half phi prime squared plus v of phi. That makes sense. The phi prime is coming from a kinetic part of the Lagrangian, associate that with the kinetic energy, and the v, that's just the potential. In the Lagrangian, it's the difference. The Hamiltonian density is really like an energy density. So for an energy density, I expect that the total energy density is a half, well, the kinetic energy plus the potential energy. That's what it is. Okay? So that's the Hamiltonian. Good. Now I'm going to put in some other information. What I'm interested in, the type of solutions I'm interested in are finite energy solutions. Now, how I get from the Hamiltonian density to the energy is by integrating it. And that's because the Hamiltonian is the energy density, which is the energy per unit volume. Then I've got to integrate it over the volume. Of course, I'm working in the real line, so integrating over the volume means integrating with respect to x from minus infinity to infinity. So that's the total energy. I want this total energy to be finite. So I'm integrating something that looks like this. The integral from minus infinity to infinity dx, a half d phi by dx squared plus v of phi. The only way I can get this energy to be finite is if these quantities here both vanish at infinity. That makes the integral finite. So the way this works is that I get finite energy solutions if I make sure that d phi by dx goes to 0 as mod x goes to infinity, and v of phi goes to 0 as mod x goes to infinity. Okay? So those are two conditions that the requirement of finite energy has imposed on whatever system I'm trying to study. Anything that I solve, I've got to bear this in mind. Yes? What if v is negative and cancels off the d phi squared? Well, if v is negative, then you have the yeah, that's right. Okay, so it can cancel off the kinetic part, but for the type of systems that we're interested in, it's only the finite. It's only the positive V that I'm going to be focusing on. So, I mean, right, there's a way of thinking of this in terms of a particle motion on a negative potential, but that's just not going to. Yeah.
Earlier, when you're finding your Lagrangian, you're using the fact that the boundary terms disappear, which is going to force it to d phi x has to go to 0.
In doing this integral here, the boundary term is going to be delta phi times d mu phi. So I have two options. Either d mu phi vanishes at infinity or the delta phi vanishes at infinity. And what I usually assume is that my variations at infinity vanish. So that'll kill off that. So this really is a separate condition. Okay, so we'll keep this aside for the moment. Now, what I really want to do is evaluate this constant. And I've just said that at spatial infinity, d phi by dx goes to 0, as well as v of phi goes to 0, if I'm going to get finite energy solutions. So if I evaluate this thing at spatial infinity, so if I evaluate the left-hand side at x equal to infinity, I get 0. Because this is vanishing, and so is this. Okay? But this is a constant. And if that constant happens to be 0 at spatial infinity, it's got to be 0 everywhere else. So the upshot is that that constant is equal to 0. So what we found then is that a half d phi by dx squared minus v of phi is equal to 0. Okay? Which means that v of phi, the potential, is really 1/2 of d phi by dx squared. But that's good because I can solve this guy. Right? If I solve for phi from there, I'll find that phi, phi is equal to the integral with respect to x of 1 over the root of 2 v of phi of x. Sorry. Nonsense. Let me do this again. So d phi by dx, that's 2 d phi by dx is equal to square root of 2 v of phi. So because I'm only interested in static solutions, effectively this is just a function of x. I'll make those total derivatives. And now it's a separable equation. And I know how to solve separable equations. This says that dx is equal to d phi over root 2 v of phi. And then I integrate this guy, and I integrate this guy. And on this side, I get x minus x naught. And on this side, I get the integral of d phi 1 over 2 v of phi. So this tells me how to solve for x once I tell you what the potential is. I give you the potential, you integrate the potential, and you'll get x as a function of phi. And then you invert that to get phi as a function of x. And that's it. You've solved the equation, subject to these conditions. Okay? Good. So the one thing that I haven't said here is that I've taken a square root. So wherever I take a square root, I've got to throw in a plus or a minus. So there's actually two solutions here, one with plus and one with a minus. Now, up to this stage, I haven't said anything about the potential. all that I need of the potential is that as mod x goes to infinity, v of phi goes to 0. So, can I think of a potential that will have this property? You've already been told one of these things the other day in Malik's lecture. That was this Mexican hat potential. Only he was interested in the Mexican hat potential in two spatial dimensions. Or, well, the picture that he drew was with two spatial dimensions, and this was really a Mexican hat. This is just in one spatial. He drew a Mexican hat potential where phi had two components. So that's why he had another axis down here. What we're interested in is something like this, where phi, this particular v of phi, has two minima. We'll put the minima at plus f and minus f. Okay? And at plus f and minus f, v of phi is equal to 0. Okay? The form of this potential is lambda over 4 factorial phi squared minus f squared all squared. So that's this symmetry breaking Mexican hat type potential that you're familiar with. Okay? Now, what I've said here is that as x goes from minus infinity, as mod x goes to infinity, v of phi must go to 0. Which means that if I start my field, if I think of the field as a ball rolling in this potential, then if the ball starts rolling here, or rather, if the ball finishes rolling here as x goes off to infinity, then it satisfies this condition that as mod x is going to infinity, v of phi is going to 0. So the field takes its values down at the bottom here. Okay. So this is the form of the potential. You can take this form and you can plug it into the equation up there, and you can integrate it. So let's do that. What we want to do is find the integral d phi 1 over the square root of 2 times v of phi. So that's root 2 times lambda over 4 factorial. 4 factorial is 24, so it's lambda over 12 phi squared minus f squared squared. That's a pretty elementary integral to do. I'll leave it as an exercise. To show that what you get is two times root 3 over lambda f squared the inverse hyperbolic tan of phi over f. So I can call this thing under the square root sign here. Let's just call that 1 over m for reasons I'll explain just now. So at the end of the day, we have 2 over m arc hyperbolic tan phi over f is equal to x minus x naught. Okay? Which means that phi is equal to f times tan, a hyperbolic of m over 2 times x minus x naught. But really, there's a plus or minus here, so I have two solutions. Both plus and minus f hyperbolic tan of m over 2 x minus x naught are solutions. So that's an exact solution. I've solved an equation of motion that looked like this, with v of phi looking like this, subject to those boundary conditions, and I've got an exact solution. It's a hyperbolic tan. So what are the properties of the solution? So the kind of questions we can ask ourselves are the following. What does this look like? Why did I call this particular bunch of constants 1 over m? If I just invert it, why did I call it m? Why m? And 3, what's so special about the solution? Okay. Well, let's look at the first question. Let's see if we can. It's hyperbolic tan. We all know what a hyperbolic tan looks like. Hyperbolic tan has the behavior that as x goes off to infinity, hyperbolic tan goes off to 1. So phi is going off to infinity. Phi is going off to plus or minus f as mod x goes to, as x goes off to infinity, and as x goes off to minus infinity, tan hyperbolic goes to minus 1. So the signs become switched around. So phi goes to minus plus f as x goes to minus infinity. For concreteness, let's just pick one sign for the moment. Right? And then I know that the way hyperbolic tan behaves is that phi at x equals 0, that's just equal to 0. So, what I have is a smooth function, because of course the other thing that I'm assuming here is that my solution is not singular. So I have a smooth function that interpolates between minus f and plus f. So it starts off at x equals minus infinity at minus f, and then it sort of smoothly does this. So that's what my solution looks like. And plus f is characterized by it gets small. So if I'm large here, in the hyperbolic tan, and it's soliton in inverted commas. Tell you why just now. The key thing to note about this kink is that its kinkiness is localized. Right? It's really this region here that's important. Of course, what I haven't told you here is that I've set x not equal to 0. So where it cuts the x-axis is really its location. And there I've set x naught equal to 0, but I can change x naught. If I change x naught, I can move it back and forth, and then it becomes localized about the point x naught. Okay? But the thing is that it's localized. So how do I know that it's localized? I mean, I can look at it and tell you that it's localized. But you can think of this thing as some sort of radioactive particle. And the way to detect where a radioactive particle is localized is you take a Geiger counter and listen to the ticks. And where you get the most ticks is where it's the most energetic, and that's where it's localized. So one way to see that this thing is localized is to calculate its energy density. And its energy density, I said, was nothing but the Hamiltonian density. The Hamiltonian density is just a half phi prime squared plus v of phi. But of course, this first integral of the motion of phi tells us that v of phi is nothing but a half phi prime squared. So I get 2v of phi. Or, equivalently, 2 times a half d phi by dx squared. But I know what phi is. Phi is just hyperbolic tangent. So I know how to differentiate phi with respect to x. That'll just give me hyperbolic secant squared. And then the energy density is just the square of that. So the energy density then goes like hyperbolic secant to the 4th power. So it's m squared f squared over 4 times sec to the 4 of m over 2 x minus x naught. What does hyperbolic secant look like? Well, hyperbolic secant looks like this. I can actually, let me plot this thing on the same system of axes. So that kind of looks like this bell-shaped thing. Okay? This is the energy density. Great. Now, if you look at the energy density is certainly localized around x naught. Okay? So in some sense, this kink is like an extended particle of some sort. I mean, it's still got to satisfy a whole bunch of other particle properties, and we'll come back to that just now. But more or less, it's like some sort of extended particle. But the key thing about this is that its equation of motion is a wave equation. So I've taken a wave equation and I've solved it, and I've got this particle-like solution, which I'm calling a soliton for the moment. It's actually not a soliton. It's a solitary wave, and the reason is because when we talk about solitons, we talk about localized, finite energy, non-singular, self-supporting objects. But they're localized, finite energy, self-supporting objects that survive collisions. I'll tell you how these things collide just now. But if I take two of these kinks, if they were solitons, and I made them collide, they just pass straight through each other. So that doesn't sound too spectacular, until you realize that what you're dealing with here is a nonlinear system. And that's really key to this whole thing, is that this is a nonlinear system. The kink is a nonlinear object. And nonlinear systems are really weird. If you take two nonlinear objects, and you put them together, you don't superpose them. You can't superpose them. The principle of superposition is a linear thing. It doesn't work in a nonlinear theory. So if I take two objects, and they have amplitude, say, 2f each, and I put them together in a nonlinear system, I'm not guaranteed that they'll pass through each other. Lots of weird things happen when they collide. And I'm not even sure that they'll survive the collision. Solitons do. If I take two solitons, these are solutions to a nonlinear system, but they behave linearly in that sense. If I take two solitons and I collide them together, they survive the collisions. They come out with maybe a phase change, but that's about, that's the worst that can be. The same is not true of the kink. If I take a kink and I collide it with another kink, it does not survive the solution. In fact, it's not even a solution. It doesn't satisfy the same boundary conditions. If I take a kink and an anti-kink, which, by the way, looks like this, it's just the minus of this guy. If I take a kink and an anti-kink, and I collide them together, they don't survive the collision. I actually have sort of nice maple animation to illustrate this, but I didn't bring my computer. But they don't survive the collision. Okay? So they're not solitons. So what are they? They're not solitons per se. They're what's called solitary waves. The properties that we extract from this thing is that the phi-4 kink is finite energy self-supporting, meaning it doesn't, if I just take this lump of energy and I stick it there, it stays there. It doesn't disperse. So it's self-supporting localized solution. Okay? Key here is finite energy, self-supporting, localized. Right, so I said that what I have really is just a lump of energy sitting there. Okay? So it looks a little bit like an extended particle of sorts. And in fact, when I was labeling some of the constants that describe the solution, I specifically chose something and I called it M. And M we usually reserve for mass. Let me show you why it is that I did this. Now, if I look at this potential, and I take the field value at the minimum, at one of the minima of the potential, say phi equals F, and then I perturb this field slightly around that minimum. So you can think of the field as a little ball sitting here, and what I do is I push it and I see what happens. So I consider little perturbations around that minimum. So what I do mathematically is that I consider phi equal to F plus something small. And that something small I'll call eta. And eta can take values that depend on x. So eta is a function of x, and F is just f. That's just a number. So I consider little perturbations around this minimum. Then I say, well, what happens? Well, you'll notice that in the Lagrangian, well, if I take derivatives of this guy, d mu phi is just d mu of f plus eta. F's a number, so this thing is the same as d mu eta. The other thing I need to worry about is what happens to v of phi. Well, v of phi goes to, that was just lambda over 4 factorial times phi squared minus f squared, all squared. That becomes lambda over 4 factorial times phi squared is now f squared plus 2f eta plus eta squared minus f squared. And then I've got to square this whole guy. These two things cancel. And if I square that, I get lambda over 4 factorial times 4f squared eta squared plus 2 times 2 is 4f eta cubed plus eta to the 4th. Which is then lambda over, so that's 4 there, that'll cancel with that, then there's 6, and 6 is 2 times 3, f squared times eta squared plus some other junk which I don't really care about. Okay? And then from Professor Z's lectures, which in principle I actually wasn't attending, but you probably remember that the thing that sits in front of the quadratic term you identify with the mass of the particle or the field. So the mass always appears like a half m squared phi squared, or m squared something squared. I look at the quadratic term, I read off the coefficient, and that'll tell me what the mass is. So that's why I call this coefficient, this combination of the constants in the phi-4 theory, m squared. It really is the mass of this object. It's not the mass of the kink, though. The mass of the kink we calculate differently. The effective mass of the kink you calculate by calculating the area under this purple curve. Remember, the purple curve told us what the energy density of the kink was. We found that the energy density was localized around x naught. The area under the energy density is just the integral from minus infinity to infinity dx of the energy density. The integral of the energy density is the total energy. So the total energy of the kink, the area under the curve, is otherwise called the classical mass of the kink. That's the effective mass of the kink. And as an exercise for you, you should go off and compute the compute M classical. Okay? All right. So far we have a classical mass for this extended particle-like object. Now, you remember earlier I told you that this was a relativistic theory. It was a Lorentz invariant theory. If I find a solution of the thing in one frame, I can boost to another frame by a Lorentz transformation, and that solution will remain a solution. What I need to know is how does it change? Firstly, this is a scalar particle. Well, it's a scalar field. And scalars transform like scalars. Which means if I make a boost to this thing, the only thing I need to do is replace the coordinates by the Lorentz transform coordinates. How do Lorentz transformations work? Well, from your first year of physics, you know that if I make a Lorentz transformation on x, x goes to x minus vt over the root of 1 minus v squared in units where c equals 1. That's a Lorentz transformation. So to boost the soliton, just soliton-ish thing, to boost the kink, which is a static object, all I've got to do is replace x minus x naught with x minus x naught minus vt over 1 minus v squared, or the square root of 1 minus v squared. That makes it move. Okay? So the moving phi, which is parameterized by its velocity v, and is a function now of x and t, is plus or minus f, hyperbolic tangent of m over 2 times x minus x naught minus vt over the square root of 1 minus v squared. Of course, I have the restriction that v lies between minus 1 and 1, so that this guy actually moves slower than the speed of light. That's the moving kink solution, the boosted moving kink solution. But if I'm trying to identify this guy with a particle-like object, then it's got to respond to Lorentz transformations like a particle would. And I know that if I take a particle and I boost it, so I make Lorentz transformations, what happens to this thing is that its mass changes and its length changes. So I've got to try and identify the same sort of thing in the kink. So to do that, what I need to do is tell you what happens to the width of the kink. When I wrote down for you earlier the picture of the kink solution, we found that the characteristic width of the kink was 1 over m. And it starts getting square contracted. Is phi dot squared plus everything else I, of course, know what phi dot is because I can calculate it from here. I should actually put this in. And then you can go ahead and calculate the effective mass of the moving kink. And if you do that, you'll find that the effective mass of the moving kink, again, this is an exercise you should do, is the square root of 1 minus v squared times m classical. So what happens there? Well, as v increases, this number's getting, 1 over. As v increases, the square root of 1 minus v squared is getting smaller and smaller. So the effective mass is getting larger and larger. Again, this is typical of what we'd expect when we take an object and we Lorentz transformation. When we apply a Lorentz transformation to it, we Lorentz boost it, its mass increases. Yes?
Is that inverse relationship between the width and the mass a generic thing?
What do you mean?
Well, I mean...
Well, if you look at right. If you take this ruler and you boost it in that direction, then it gets Lorentz contracted.
Sure.
And its mass increases. So its width decreases and its mass increases. That's not a property of the kink. Right. Yeah. So that I'm not sure if that's is that what we're asking? Okay. Right. Yeah. Yes.
Is that partly the way they achieve Soliton propagation for fiber?
No, actually, no. So in fiber optic cables, the differential equation that governs what happens there is a completely different differential equation. So one of the things that it's the nonlinear Schrodinger equation. Okay, so it's something that looks like the Schrodinger equation, except it's a non-relativistic equation. And the pulses in the fiber are solitons in the nonlinear Schrodinger equation. But those are actual time-dependent solutions. What I've done here is construct a time-independent solution and then sort of trivially extend this to a time-dependent solution by just boosting it. And that's because of the symmetry that's inherent to the theory that I started off with. Right? With the nonlinear Schrodinger equation, I can actually construct time-dependent solutions. So what happens in fiber optic cables with Soliton propagation in these fiber optic pulses is something different. It's a different solution to a different equation.
Jeff, just one comment that I wanted to make is if you look at the solution, it's actually the only energy scale that you have. So in units of h bar equal to 1 over n would be the only length scale that you have. So it's not surprising that you see that relationship here. But I guess if there was a theory with more than one length scale or more than one energy scale,
You see a difference.
who knows what would
Yeah.
happen there.
How do you calculate the characteristic width of differential or of the particle?
Well, how you calculate it for this is one way of calculating do actually. Is the negative solution. Yeah. So the pink curve is the kink and the yellow curve is the anti-kink. Okay. Now, how many points have I made? 2. Right. Okay. The other thing to note here is that you see there's an M here, and M went like. Right, so M is equal to the square root of, it's equal to the square root of lambda times F over the square root of 3. Okay, so F here is equal to root 3 M over root lambda. If I take that F and I plug it into here, I get a 1 over root lambda sitting in this solution. What is lambda? Well, lambda controls the nonlinearity of my system. If I go back to the potential, I can turn the nonlinearity off by turning off lambda. I send lambda to 0, and it then becomes a linear system. But then I look at the solution, and because there's an F here, which goes like 1 over root lambda, goes like 1 over root 3, and you can turn 3 off. It goes like 1 over root lambda. If I send lambda to 0, the solution's singular. It blows up. What this means is that the kink is really, truly a nonlinear object. I cannot take the linear theory and make a perturbation series in lambda and hope to find the kink. It's a nonlinear object, and that's really absolutely important that's probably one of the most important things about the solitons. They're 100% nonlinear objects. Now, the last point that I want to make before we go to lunch on time for the first time, in an amount of energy to do that is not a dynamical stability. It's not stable because of some of the dynamics that it's undergoing. It's stable because of some topological property. And these classes are all labeled by pairs of. And what this tells you as x equals minus infinity, and where it ends minus infinity and phi at plus. So a kink, anti-kink system. So I've split the space of finite infinity, which is f, minus infinity, which is minus f. So there's f minus f, that's 2f. And then I divide by 2, so I should actually put this because I know it should be 1. Okay, so 1 over 2f times the field value at infinity minus the field value at minus infinity. So for the kink, the charge comes out at 1. And I know that if I have a charge, then I can associate to that charge some conserved current. Okay? The conserved current that I associate to this charge goes like 1 over 2f epsilon mu nu d nu phi. Where epsilon mu nu is the totally antisymmetric tensor, which means that epsilon 0, 1 is equal to plus 1. If I interchange these two indices, then I get epsilon 1, 0, and that's minus 1. So this is the property of the totally antisymmetric tensor. And K mu, the conserved charge associated to this the conserved current associated to this topological charge, is 1 over 2f epsilon mu nu d nu phi. Now, if I go and calculate K mu d mu, right, this has one vector index. So what I'm doing here when I contract these two is I'm finding the divergence of this current. If it's a conserved quantity, then this divergence must come out to be 0. Let's see if that's true. Well, that's just 1 over 2f epsilon mu nu d mu d nu phi. And the reason I can do that is because this is a constant, of course. Right. So what I have here is a totally symmetric quantity contracted with a totally antisymmetric quantity. What?
That one's symmetric.
Sorry, the other way around. Totally antisymmetric, totally symmetric. When you contract a totally antisymmetric object with a totally symmetric object, you get 0. If there's nothing else you remember from this lecture, remember that. Okay? And just because I can, I'll leave this as an exercise for you to solve. That's.
No, I was just going to say that for those still learning index notation, it's worth just writing out all the possibilities and seeing that it has to be there.
Oh, okay. That's
essentially the index.
right. I was going to just interchange the two indices and then show that.
The other thing then is to try it out.
I'll leave it as an exercise. It's fine.
I'm just saying it's a nice simple thing. There are only two values the indices contain.
That's right, yeah.
It's worth really exploring in all the different ways.
Okay. Might as well. Right, so these can only take two values, so that's 1 over 2f. So the exercise is really to show this in a better way. Right? It's 1 over 2f.
Oh, sorry. I didn't mean that you were to do it.
Oh, I see. Good. Right, okay. That's right. So, and then you can see that this topological charge that we had, 1 over 2f, is nothing but the integral from minus infinity to infinity dx of k naught. And that's how you normally get charges. You take the time component of the current and you integrate it over space, and that gives you the charge. So I have a topological number that characterizes this kink solution. That number must be conserved. So I cannot deform a kink to an anti-kink, because an anti-kink has q equals minus 1, and a kink has q equals 1, and they're no longer conserved. So this is a conserved quantity that I associate with this soliton-like object. Okay? Unlike conserved quantities that you've seen before, like energy, momentum, angular momentum, those are all associated to continuous symmetries of the theory, like time translation, space translation, rotation symmetries, as you got from Robert's lecture. Here, the conserved quantity is not associated to any of the dynamics. It's associated to boundary conditions. It really comes about because the field takes one value at spatial infinity, at x equals plus infinity, and another value at x equals minus infinity. Now, everything that I've told you today applies for a really, really simplistic system. It's 1 plus 1 dimensions. It's one scalar field. There's no other fields in the problem. But this is a soliton-like object. It's a solitary wave. Okay? Everything that I've said, you can actually extend to higher dimensions. You'll run into problems because immediately as you go to 2 plus 1 dimensions, you find that there's a no-go theorem that says that you can't do this anymore. But you can overcome that. And you can extend this to theories with more fields, to theories with various other symmetries, internal symmetries. You can extend it to objects in string theory. So you can find solitons. In string theory, you can show that you can make these things spin and they can still find solitons. They're absolutely universal. This is the simplest system that I could think of to demonstrate all the necessary properties that you'll find in these high-dimensional systems. And I hope that you actually learned something from it, and this is interesting enough that you'll go and look up the reference that I gave you at the beginning of the lecture and try to learn something more about solitons. Thank you.